Hi everyone. In this work, we introduce a new approach for structuring dependent concepts into hierarchies that can facilitate learning processes. In multi-class classification tasks, it is often assumed that classes or concepts are separable. In real-world applications, however, this assumption becomes strong and generates inconsistencies. This is particularly true in the case of human activity recognition from wearable sensors. For instance, are the criteria used to distinguish between the activities, for example, running and walking, the same as those used to distinguish between driving a car and being in a bus? Uh, Similarly, during the dataset annotation process, for example, when should someone consider that walking at a higher pace corresponds actually to the activity running and not to walking? All these questions naturally arise in real-world datasets that we consider in our work and which exhibits such dependencies. The considered activities in this data set are difficult to separate due to the existence of many overlaps. During the learning process, the most commonly used approach is to learn classes one by one against the others. But this computational simplification principle introduces strong inductive biases on the learned theories. And in fact, the natural connections among some classes and not others deserve to be taken into account. Well, to do this, one natural approach is to structure the considered concepts into hierarchies in a way that very similar concepts are being grouped together and tackled by specialized learners. Well, the idea is that the learning and classification at different levels of the hierarchies may rely on different features or different combinations of the same features. Well, now, the problem at hand with this approach is twice difficult, as we have to first find the most appropriate hierarchical structure, and second, find optimal learners which are assigned to the nodes of the hierarchical structure. So how to generate the most appropriate hierarchy, how to find these groups of similar concepts, at which depth should we stop forming groups of concepts, so on and so forth. Well, a naive approach would be to generate and test the latest structure of all concepts and to choose the three hierarchies which give the best accuracy for the set of atomic concepts that we consider. But in practice, this is not sustainable because of the exponential number of possible trees. And by the way, this number can be described by the recurrence relation here, which involves binomial coefficients to compute the total number of tree hierarchies for k different concepts. In particular, the first few number of tree combinations for one concept, two concepts, and so on are illustrated here. In the case of the real-world dataset that we use in our work, and where we have 8 different concepts, the number of different hierarchies for this case is more than 600,000 hierarchies. So to deal with this computational bottleneck, we propose an approach based on transfer affinity among the concepts in order to determine an optimal hierarchy for the learning process. Our solution involves several repetitions of 3 main steps. The first step is concept similarity analysis, where we leverage the notion of transferability between concepts, and which allows us to obtain a set of affinity scores which measure the dependency between concepts. The second step is hierarchy derivation, which uses the obtained affinity scores from the previous step and produces a hierarchy by means of an agglomerative clustering approach. The derived hierarchy is then assigned with learners, which are trained and further refined to adjust the hierarchy structure. These steps are detailed in the following. So in the first step, we leverage, as we said, the transfer affinity between concepts as a measure of similarity. In other words, let's take a model or an encoder trained to learn a given concept. Well, the easier this model can be transferred to account for another concept, the higher the similarity and dependency between these concepts. So besides the nice empirical properties of this measure, which have been, by the way, investigated in various fields like computer vision and natural language processing, the motivation behind relying on this notion of transferability is to reuse what has been learned so far while deriving the hierarchies of concepts. So this step results in, at the end, in an affinity matrix which captures the notion of transferability among the considered concepts. So for this, we first compute for each concept Ci an encoder that learns to map the input samples labeled as Ci to a latent representation Z subscript Ci. So learning the encoder's parameters consists in minimizing the reconstruction error, which satisfies the optimization objective that we can see here, where F is the encoder, and on the other hand, J is a decoder which maps back the learned representation into the original input space. Note that this step does not involve any target concept. Now we compute the affinities between the concept Ci and each of the other concepts. For this, we use the learned encoder for concept Ci, and we compute affinities with other concepts via fine-tuning of the learned representation. Well, precisely, we still have the encoder F from the previous step, which was trained initially on the concept Ci, and we fine-tune it to account for another concept Cj. This process consists similarly as before in minimizing the reconstruction error. However, now, rather than using the encoder J learned above, we design a genuine decoder which is trained on the target concept Cj. The initial learned representations are fine-tuned using a batch of samples from the considered target concept, and we refer to the number of examples belonging to the concept Cj, which are used during this fine-tuning step, as the supervision budget, and we denote it by B. And the final score and the final similarity score is computed by considering the supervision budget in order to account for its impact during the hierarchy derivation. Here, the affinity scores are depicted by the arrows between concepts. So the thicker the arrow, the higher the affinity score. And in particular, we can see the high affinity scores obtained from the concept similarity analysis, which are highlighted by the red arrows. On the other hand, here we can see that concepts like 4 and 7 or 3 and 6 have a low affinity score. Now, given the set of affinity scores obtained previously, we derive the most appropriate hierarchy following an agglomerative clustering method. This agglomerative clustering method proceeds by a series of successive fusions like these, using the recurrence formula depicted here, and results in a structure represented by a dendrogram that you can see here. For any non-leaf node of the derived hierarchy, we associate a learning model that encompasses an encoder that maps the inputs to their corresponding latent representations, and an empirical risk minimizer, or ERM, that outputs decision boundaries based on the representations produced by the encoder. The question that remains here is which encoders to use in these non-leaf nodes, whether all children are leaves or at least one child is a non-leaf node. It is not clear which encoder to use in either cases. So this is why we perform an additional step called hierarchy refinement, which is responsible of selecting the best encoder to use in each non-leaf node. In this step, the hierarchies are being adjusted by a series of transformations that are performed on the non-leaf nodes, as depicted in this example. At the same time, the weights of the assigned models are adjusted in order to account for local errors, and the process is repeated until we converge into a satisfactory solution. This brings us to the experimental part of our contribution, where we evaluate our approach on the SHL dataset, which provides multimodal and multi-location data recorded in real-life settings. And among the considered activities, we have still walking, running, biking, driving, or being in a car, and so on and so forth. The autoencoders that we saw before were constructed by stacking different one-dimensional convolutional layers, whose hyperparameters were optimized using the Microsoft NNE toolkit. And for reference, the obtained results are compared against a baseline which uses a flat classification setting. The proposed approach was evaluated following 3 different axes, and in the following we will detail the 2 first axes with some noticeable obtained results. So first of all, evaluation of the hierarchical classification performances. This figure here concentrates on the resulting per node performances. In other words, how accurately the models associated with the non-leaf nodes can correctly predict their associated concepts. The nodes are ranked according to the obtained per node performance, and they are accompanied by their respective appearance frequency while repeating the experiments. Well, it is worth noticing that the concept still, learning alone against the rest of the concepts, the first bar here, achieves the highest gains in terms of recognition performances, while the appearance frequency of this learned configuration is high, more than 60 times, as you can see here. We see also that the concepts bike, car, and bus grouped together, the 5th bar here, occur very often in the derived hierarchies, which is accompanied by fairly significant performance gains with 5% on average. On the other hand, here we assess if the performance improvements we got previously at the node levels are actually reflected at the concept level. The experiments here show the recognition performances of each concept averaged over the whole hierarchies that we derive using our proposed approach. And overall, we indeed observe that there are significant improvements for each individual concept over the obtained results from the baseline. Here, the question that is discussed is related to the separability of the concepts that are grouped together. Well, one of the most important properties that we are seeking in our approach is whether concepts with high affinity scores lead to separable representations. The figures in the right illustrates the decision boundaries generated by the considered ERMs, which are provided with the learned representations of 2 concepts, Ci and Cj, depicted in the right hierarchy here. In the first case, when the concepts Ci and Cj exhibit a low affinity score, putting them together results in a poor separability, as illustrated by the ERM's decision boundary in the top right figure. On the contrary, when these same 2 concepts exhibit a high affinity score and we put them together, This results in a good separability and gets a fairly distinct frontier, which is illustrated in the bottom right figure. Another important aspect that is investigated in the empirical evaluation is the impact of the supervision budget discussed above, used to fine-tune the initial representations. In particular, we take a look at the relation between the initial affinity scores and the amount of supervision and how all this impacts the final classification performances. And most noticeably, this figure shows that increasing the supervision budget to some larger extents, for example, more than 300 examples, results in a substantial decrease in classification performances of the ERMs. This shows that a trade-off between separability and the initial affinities arises when we seek to group concepts together. Additional results can be found in the paper. So to summarize, we proposed in this work an approach based on transfer affinity to determine an optimal organization of the concepts, which ended up improving both learning performances and accelerating the learning process. We performed extensive experiments which shows the effectiveness of organizing the learning process, and we noticeably get a substantial improvement of recognition performances over the baseline. And more importantly, the comprehensive empirical analysis raises interesting questions about concept dependencies and the required amount of supervision needed to measure the dependencies.